Okay, so in this video, we're going to talk about payment channels and off-chain channels in general. So what's the idea of off-chain payment channels? Well, blockchain transactions are pretty expensive. So as we've talked about, every transaction you make has to pay some transaction fee, and the more transactions you make, the more fees you have to pay. Also, each transaction has some latency, right? And it's even worse than that because there's actually limited capacity to most blockchains. Because the whole point of a blockchain is that it's a distributed network, there's multiple nodes that are in replication, validating every transaction. Um, Depending on how many nodes are available on the network, how many resources there are, there's some limit to how many transactions can be processed. Different networks have different limits, and it depends on the design of the network, whether it has some feature like sharding or committee selection. But anyway, any given network is going to have some capacity of transactions. And we've seen what happens in several cases on both Ethereum and in Bitcoin. In Ethereum, really notably, during December 2017, there was a really popular smart contract called CryptoKitties. And this was one of the first times that people really noticed there was so much demand, so many transactions going to the CryptoKitties game, that it actually started to bog down the Ethereum mainnet network. This has happened at other times during rushes to get in on an ICO sale that's closing, things like that. And Bitcoin has at several times had periods of congestion due to there being more transactions than the network's capacity was. So what happens in a cryptocurrency like Bitcoin and Ethereum anyway, when there's too many transactions, is that there's a backlog. And because it's up to each user to decide what fee they provide on each transaction, miners tend to process the transactions by the largest transaction fee per byte or per gas unit, and down. And so these little charts like this show that when there's congestion, the higher a fee you pay, the more likely your transaction is going to get processed soon. So the high fee paying transactions tend to be delayed for a small amount of time, whereas lower fee paying transactions have to wait until the backlog clears. And you can pay a higher transaction fee during such congestion if you want to try to get ahead of the place in line. But anyway, no matter what, due to the replication of data and of work in distributed cryptocurrency networks, there's going to be some capacity limit. And so this motivates trying to have ways of using smart contracts that don't actually require an on-chain transaction for every step you want to take. So the basic idea of the off-chain method for improving transaction scalability is to basically have a contract that you use as a dispute resolver, but that you don't use in the typical case. So what will happen is that if you want to run an off-chain channel between two parties, both of the parties will make on-chain transactions to deposit some amount of Ether cryptocurrency. And when they want to interact with each other, they'll actually be doing interactions primarily by communicating directly to each other over a socket, over some other layer, not making transactions to the blockchain, but just sending messages to each other. And what happens is that when either of the two players thinks that the other has quit, has gone away, or their network has crashed, or they're trying to cheat by sending invalid data, any circumstance like that, then the remaining party raises a dispute. And this also involves making an on-chain transaction. And the idea is once you raise a dispute, you provide the evidence that you have, and the code of the smart contract determines what the outcome should be. And in particular, it decides how much money to give back to the two corresponding parties. So this is the basic idea of off-chain methods. You do some setup transaction, you do some closing transaction, but for the most part, you just do interactions off-chain. In slightly more detail, this is an example of one such off-chain application. It's the simplest one. It's a unidirectional payment channel. And so here the idea is that Alice wants to make micropayments to Bob. So Alice picks a maximum amount of money that she wants to send of these micropayments. Maybe she wants to, the example I like is that Alice wants to pay for streaming Wi-Fi service from Bob. And so Alice wants to pay a tiny amount of Ether every half second or so, as long as the Wi-Fi link is still working and sending packets. And what we want is for Alice to only have to make one transaction at the beginning. Clearly, she's not going to be making a new on-chain transaction every half second. But what we want is that either party at any given time is guaranteed that they're able to get the amount of money that they want, that they expect. So in this scenario, Alice wants to pay a little bit amount of money to Bob every half second. She deposits $10 initially. This is going to require one on-chain transaction. And now every time Alice wants to send Bob a slightly larger payment, essentially what she's going to be doing is sending a signed message, signed with her key, on a slightly larger value. So here I have one signature from Alice that signs the message $1, and she sends this signature off-chain to Bob. When she wants to spend a higher amount, she signs a larger number, like here she signs the number 2, right, for $2, and she sends that to Bob. And now what happens is that at any time when Bob wants to settle, close the channel, withdraw the money that's there, Bob will take the highest signed value, like the signature from Alice that he's received on the largest monetary value, and he'll include that signature and data in the message that he sends to the blockchain. All right, now the security goal here is that we want to be able to protect Alice from Bob taking more money than she intended to pay, and we want to protect Bob from Alice trying to take a refund that Bob thinks that she actually paid. And so because Bob has these signatures from Alice, he's able to make the transaction that has the largest value signatures that he's had. That's what protects Bob. And what protects Alice would have to be a final condition, which is some timeout clause, which is basically if Bob goes away, then Alice can take all of her money back after some time limit. Okay, so to give a concrete example of this payment channel idea, I am illustrating here some pseudocode. It's not exactly in Solidity syntax, but it's pretty close for implementing the unidirectional payment channel. So there's really only two methods here, and only one of these methods is typically called this finalize method. Notice that since the contract is only defining the dispute handling procedure, there's no method for every payment because most payments proceed off-chain. They don't involve the smart contract at all. So you really only interact with the smart contract when creating it and making a deposit and then finalizing it. So here I'm assuming that Alice and Bob are both member fields. They would have been set at the time the constructor for this contract was run, and that there's already some balance which was deposited at the time the contract was created. So now the finalize method would be called by Bob. That's checked by having require message.sender as Bob. This implicitly is checking the signature for Bob's key. Now the parameters to this finalize method are the amount and the signature. And the idea is that the signature is checked in the second line here, is checked to correspond with Alice's public key. So this signature has to match the amount that's passed as the argument to the method called by Bob. So essentially we're checking both signatures, a signature from Bob implicitly through message sender and a signature from Alice explicitly here through verify signature. If the signature from both of them check out on this amount, then we transfer the given amount to Bob, and whatever is remaining in the contract we transfer back to Alice. Now, as I mentioned, we have to have a refund condition here that protects Alice in case Bob disappears. And so what we say is, here Alice has to call this method with that require statement. And in order to make it so Alice can't take a refund too early, Bob has a chance to call finalize himself. We say that this refund has to take place after a deadline that was set. So we check it here by this block number. And if so, we transfer whatever is the balance back to Alice. Okay, so this was a simple unidirectional payment channel. There's a generalization of this idea that's the duplex payment channel. And so it's the same basic idea. We have a payment channel for two parties. They both, some combination of them, deposit some money into it. They can pay each other now, so it's not just one party paying the other, but instead they can take turns paying each other back as frequently as they want, only exchanging signatures off-chain. And in the same case, when one party wants to withdraw or close the channel and settle out, or they just think the other party has crashed or is failed in some way, then they invoke the dispute method by sending a transaction to the payment channel contract. So the code for the duplex payment channel contract is a little bit more complicated. And basically, it's a little more complicated because it has to handle a case where one of the parties tries to replay an earlier amount for which they had already agreed on, like both of them had sent their signatures. It's a little bit complicated, but let me try to explain it. Suppose Alice and Bob each start out with a balance of $5. Alice receives $5 of payment, so now she would be able to withdraw 10 and Bob would have none left. Let's say that happens on Monday. And now say on Tuesday, Alice pays Bob $10, so now Alice has $0 and Bob would have 10. Now what could happen is, suppose Alice she preferred the way things were on Monday because she had $10 more. So she tries to finalize the contract with her signature from Bob on Monday's amount, which gives her all of the money. Well, because Bob has a signature from her authorizing a payment on Tuesday for the $10, so really it's Bob who should get all $10, we need a way that Bob can put the higher value amount even though he had previously signed an even smaller value to him since it was all of the money to Alice. Anyway, it's a little complicated. I'll give a link to a better description of this. But basically, the way that we handle this case is by adding an additional serial number. And so we collect signatures from both Alice and Bob, not just on the amount, but on a serial number as well. So that way the serial number always goes forward, even though the amount may go up or down depending on who's paying who. But ultimately we need a signature on both parties in order to withdraw whatever is the highest serial number for which we have both signatures. So this is a little pseudocode illustration of a way of handling that, and in the video links we'll include a walkthrough of the slightly more complicated duplex channel case. Now I also have, for another video, implementation of a tiny duplex channel in Remix as an actual Solidity contract, and so in another video I'll give a walkthrough of how to actually use this Solidity code and interact with it by making signatures through MetaMask. So what's the big deal about payment channels? Well, if you just have a payment channel, the only reason you wouldn't want to create a payment channel to everyone you would ever want to pay is because you have to spend some transaction fee to create the contract initially, and you have to make this deposit of whichever ether you want available as collateral in deposit on this payment channels. So what's really exciting about payment channels is the potential to make a network of off-chain payment channels. So here we have a scenario where Alice is on the left, and Alice wants to make a payment to Bob, who's on the right. Now Alice and Bob don't have a payment channel directly between each other, but they have a pair of friends to whom Alice has a payment channel to one person, they have a payment channel to another, and that person has a payment channel to Bob. And what we want to be able to do is to route payments along this chain, each party making an off-chain payment on their corresponding payment channel to the party to their right, such that Bob eventually gets the money. Now actually implementing this is one level more complicated than the duplex payment channel, because what we want is the ability to do an all or nothing atomic payment. So basically we don't want these parties in the middle to get stuck making an outgoing payment so they lose money but not receiving the corresponding inward payment. And so there's a technique for do this we'll include some links about called hash time lock channels. Now the appeal of this is that if we can pull this off, then in principle you could have a small world network where with only a small number of payment channels per person, like the degree of each vertex, each vertex in this graph would be a person and every edge would be a payment channel between two people with fairly small degrees, so each person only having a few amount of payment channels. You could have a network that's low diameter such that you could route a payment from any party to any other party in the network while only having some, say, logarithmic number of hops that you have to do. So this is the appeal of off-chain payment channel networks. Today there are implementations of payment channel networks like this implemented in Bitcoin called the Lightning Network, and there's already a beta of this that's in use today. And currently in development in the Ethereum world, there's a project Raiden. There's also several other projects also in Ethereum, other projects besides Raiden in Ethereum, and other payment channel projects for different cryptocurrencies based on the same idea. So that's payment channels in a nutshell. Now, the idea of using these for payment channels is a clear application, although the basic idea of off-chain channels is in use for other games as well. So there's a handful of links we know of, like Funfair, and Funfair is like a gaming-based one. There's a couple others that I've seen, and I'll include a few links that basically generalize this technique of off-chain channels for other applications besides just payment channels.